Okay, so this is going to show how to derive the Michaelis Menten equation. So in the last video, we talked about how to derive the Michaelis constant, right? And so this is going to go off of that. So remember I talked about how E times S over ES equals all of this, right? So one way to clarify that is to show that Km represents all these constants. So okay, so all this information is going to be important in deriving the actual equation. So another thing is to show that the number of enzymes present, right, the number of free enzymes present is equal to the number of total enzymes minus the enzymes that already have substrates attached to them. And that makes sense, right, because the enzymes left over is going to be the total minus the ones that have substrates bound to them. And so that's going to equal E. Now, this is important because we can actually place this new equation into E, which is over here, right? So take this, right, ES over E, or E times S over ES, right? And that's all I did. And then I plugged in this new equation for the E, okay? And so it equals Km, right? Because we showed that all these constants equal Km. So that's all I did. Just plug in. So this is E, and I said that E equals this. And from there, I just plug this into here. And then I said that it equals Km. Okay, so now if you're still with me, we're going to keep going forward. And so now from this equation, we're going to multiply each side by ES. So it's now going to be Km times ES. Okay? So from here, I'm going to distribute this substrate concentration to both of these. So it's going to be E total times S minus ES times S. And the right side is still the same. From here, I'm going to add ES times S to both sides. And so that's going to cancel out over here, and the right side is now going to be all of this. Okay, so from here, since there's ES present in both of these, I'm going to factor that out and then have ES times Km plus substrate concentration. Alright, so from here, what I'm going to do is divide both sides by Km plus S, and now we have to recall the original equation I was talking about, the initial velocity times kcat times ES, right? So we're going to use this old piece of information, and we're actually going to plug in ES, right? So I said all of this is equal to ES, so from this original equation, I'm going to plug in all of this here. So that's how we get V0 equals kcat, E total, right? E total times S, Km plus S. And we have to use another piece of old information, V max times kcat E total. Now see how kcat E total is the same as here, right? So since this is equal to all of this, we can actually replace it in the equation, and therefore we get the Michaelis Menten equation. So what's the point of the Michaelis Menten equation, right? Why did we have to go through all that work to get this equation? Well, this equation shows the initial rate of the reaction using a variable that can be measured, the initial substrate concentration, which is S in brackets, right? And Vmax and Km will be different for each enzyme and substrate combo. So that's the point, right? So the original equation was using enzyme substrate complex, and that we can't measure. But this one, it uses substrate concentration, which we can measure. So that's the point of doing all this derivation. So the actual Michaelis Menten enzyme produces a hyperbolic plot shown right here, right? This is a hyperbolic plot with on the y-axis reaction velocity and on the x-axis substrate concentration. And in the next video, I'll talk about special cases using the Michaelis Menten equation. So thank you for watching, and I hope that helped.